We're going to talk about free body diagrams, which you haven't used yet, but we're getting there in terms of making your forces into a diagram, right? So these diagrams are called free body diagrams, and it's how we show forces, okay? So these are a pictorial model of forces. Okay, in our assignment, we had different forces, but you didn't necessarily draw them out. So by drawing them out, it's going to give us a really good idea of what are our upward forces, what are our downward, what's our leftward, what's our rightward, which will help us when we set up our net force equation. Okay, what's the net force equation usually tell us? Net tells us what? The overall, not really the average, but the overall. So the ups minus the downs, or the rights minus the lefts, right? Always our positives minus negatives, okay? So this is going to give us a model. So we're going to draw a free body diagram for like every force problem that we do, okay? And so our goal is to identify every place that our system touches the external world. Any single force that's acting on our object, we have to draw a force for it, okay? And forces are given by vectors, which are what shape? Lines, more specifically, arrows, right? And they go in the direction of the motion. Okay, or the direction of the force. Okay, so these are drawn as vectors. And this labeling that your book does of vectors is silly. Okay, so I'm going to show you how we really label these. Okay, there we go into way too much detail. The force of the Earth's mass on the book, what's pulling down that book? Gravity, right? So we don't need this whole thing, right? Just FG will do. The force that the table is exerting upward on the book, what's that called? The normal force, so Fn, right? And hand on book, right? That seems silly to write out that whole thing. That's any applied force, right? Contact forces, or things where we're pushing or pulling directly on our object, I usually just call them applied, so APP for applied. You can call them force push, force pull. You can name them almost whatever you want, okay? But force applied is usually how I'll label those. Okay? So, we have to label each force. Remember, our forces should theoretically be drawn to scale. Does that mean we have to get out a ruler every single time? No, it means that they should be drawn to a relative scale. So if one force is 10 newtons, one force is 5, right? That 10 should be double the size of our 5 newton force. That doesn't play into it quite as much as it did with projectiles or with vector addition. But it's just something to kind of remember. Okay? Something that we should think about is forces always should be drawn away from our object. So we don't see gravity, even though it's going in the downward direction, our force doesn't look like this. Right? That's not how it goes. All of our forces should always be going away from our object. Okay? And you can draw the object if you want, but usually with free body diagrams, we just start it with a dot in the middle. Okay, you can get really artistic if you'd like. That's not really my style. Okay, so a dot will do. Okay, so let's try one here. Draw a free body diagram of a box accelerating in the rightward direction. We're going to include frictional forces. Okay, and there's some things that are really important here in terms of context clues. It's accelerating rightward, and we want to include friction. Okay, so here we've got a box sitting on a table, right? Really, I'm going to give it by a dot. I don't need to draw the whole box. You're welcome to do that. So first thing is, if it's sitting on a surface, what two forces do we know have to be acting? Gravity and normal force. And what do we know about those two forces? They're equal to each other. How do we know that?
Because it's not moving.
It's not moving specifically in the vertical direction. Okay, so since it's not moving vertically, that means our vertical forces need to be equal to each other. Okay, so if you are drawing your diagram and you want to show that those two are equal, right, those lines are congruency lines. Isn't that what they're called? Those little marks. Okay, so if you're trying to show me that those two lines are congruent and you want to make sure that I understand that because your drawing might not be perfect, that's a good way to do it. Okay? So it's accelerating in the rightward direction. That means there's got to be some force that's pushing it to the right. Correct? What should we call that one? Right, just some sort of an applied force. So our frictional force, should it be greater than, less than, or equal to our applied force? Less than, right? And here we don't even really care at what scale it's less than because it doesn't say how great our acceleration is.
So friction always lowercase f.
Yeah, friction is always lowercase f. Okay, force is capital F, friction is lowercase. Okay, so as long as we can understand that our applied force here needs to be greater than frictional force, that's going to tell us that we have an acceleration to the right. Okay, so those frictional force and applied force are not equal. Applied is greater than our frictional force. Okay, you don't have to include that, but if your drawing is not clear, right, you might want to include that little written thing so I know what for sure you're talking about. Okay? Okay, a car's coasting in the leftward direction and slowing down. A car is coasting in the leftward direction and slowing down. Okay, so what two things do we automatically know? Gravity and normal force. Okay, and what do we know about those two forces? They're equal. Okay, you don't have to draw the congruency lines, but you're welcome to, just to make sure you understand those two things are equal. And we know those are equal because they're not accelerating in the vertical direction. Okay, so now when something is coasting, what's the only thing that's slowing it down? Friction. Are we applying a force any longer? No, right? That means that we would have our foot on the gas pedal, which we don't. So if we're moving in the leftward direction and we're slowing down, what direction does our frictional force have to be going? To the right. Okay, so we draw a frictional force here. And since we don't have numbers to go with it, we don't really care at what scale we draw our frictional force. Right? We just know that it's larger than any applied force, which we know is nothing. Right? So the only force we have there is friction.
So you don't even draw.
You don't even draw any applied force because we don't have any applied force. The only thing that's acting, if there was no friction, right, it would just keep moving. Like your box that you showed on the first one, right? No friction, it would keep moving. But friction is slowing it down. That's the opposing force.
So we did draw an applied force because it said it's coasting.
Yes, that's right. That's just a context clue. Okay? If it said we were applying the brakes and slowing down, right, we'd have a brake force and a frictional force. Right?
So you draw this on the same side?
So if we had a brake and a frictional force, we draw force of brake and force of friction. Right? Okay, so you can have two forces on top of each other. Right? Friction would really go here. But
Is that considered in applied?
But it's applying it in the negative direction. Yeah, so it's slowing it down. Good. You could put it as force applied if you want. That's fine. Okay. Okay. Last little thing I want to talk about here is something called terminal velocity. Okay, constant velocity that's reached when the drag force, or really air resistance force, equals the force of gravity. So I have a little video here that I want you to watch. Okay, I want you to watch this video real quick. Actually, I might have you. Yeah, you're gonna have.